Tonight, we are talking about the rotary phone. Not the history class version, the real version. The one with the carbon granules and the clicking machines in windowless buildings and the women connecting your calls by hand before anyone figured out how to automate it. Most people think they understand how it worked. They really do not. It is a better story than you expect. And it is a good one to fall asleep to. If this is your kind of thing, real stories, told slowly, nothing rushed, subscribe. New one every week. It will be there when you need it. All right, let's get into it. There is an object that used to sit in almost every home in the developed world. It sat on kitchen counters, on hallway tables, on the edges of desks in spare rooms. It was black, usually. Sometimes cream or pale green or an optimistic shade of red. It weighed more than you might expect something so ordinary to weigh. And it had a dial on the front, a circle of numbered holes arranged in a gentle arc, that you were supposed to spin with your finger. Most people who grew up with it never gave it a second thought. It was just there, the way a chair is just there, the way a window is just there. You picked it up, you dialed, you talked, you put it back down. That was the whole relationship. But something remarkable was happening every single time that dial spun. Something that required a century of accumulated engineering, thousands of miles of copper wire, mechanical switches of almost impossible precision, and a network so carefully designed that it could route your voice, your actual voice, the sound waves produced by your vocal cords, across a continent and deliver them recognizably and clearly to a specific person in a specific room within seconds. All of it triggered by a spinning plastic dial and a coiled spring. This is the story of how that worked. Not the simplified version. Not the version that stops at electricity travels through wires. The real version. The one with the springs and the governors and the carbon granules and the step-by-step switches clicking through their sequences in a room you never visited, responding to pulses you generated without knowing you were generating them. It begins, as most good stories do, before anyone knew what they were building. The telephone did not arrive fully formed. No important technology ever does. What arrived first, in the 1830s and 1840s, was the telegraph, a system for sending coded electrical signals along wire, decoded at the other end by a trained operator who translated the patterns of long and short pulses into letters and words. The telegraph was extraordinary for its time, and it shrank the world in ways that people struggle to adequately describe. Messages that once took weeks to travel across a country now took minutes. But the telegraph had a fundamental limitation. It required training. You had to learn the code. You had to have an operator at each end who understood it. The machine itself was not accessible to ordinary people in the way that, say, writing a letter was accessible. You could walk into a telegraph office and hand your message to someone who would send it for you. But you could not simply pick up a device and speak to someone far away, as if they were in the next room. That idea, speaking directly to someone across a distance, was the obsession that consumed a number of inventors in the 1860s and 1870s. The most famous of them, of course, is Alexander Graham Bell, a Scottish-born inventor and teacher of the deaf working in Boston, who in 1876 received the first patent for a device he called the telephone. The word comes from Greek roots meaning far sound. The name was accurate, if modest. Bell's original telephone was a genuinely delicate thing. It worked by converting the vibrations of a human voice into variations in an electrical current, transmitting those variations along a wire, and then converting them back into sound vibrations at the receiving end. The principle was elegant. The execution, in those early years, was imperfect. The earliest telephones required you to speak loudly and clearly. Background noise was a problem. The signal degraded over distance. And crucially, in the very first deployments, the telephone lines connected exactly 2 points. You had a phone. Your business partner across town had a phone. There was a wire between you. You could call each other and only each other. This was useful, certainly, but it was not yet a network. For a telephone to become truly useful, for it to justify the infrastructure required to install it, you needed a way for any telephone to reach any other telephone. And for that, you needed something that would take decades to properly solve, and that would, in its earliest form, require a human being sitting at a switchboard, physically connecting your call by hand. Those were the operators. And their story comes later, because first it helps to understand the problem they were solving. When telephone exchanges began to appear in the late 1870s, the first commercial exchange opened in New Haven, Connecticut in January 1878, serving a modest list of 21 subscribers. The system worked like this. Every subscriber had a line running into a central office. At that central office, all the lines terminated on a large board fitted with sockets. When you wanted to make a call, you would pick up your phone and signal the operator. At first by turning a small hand crank on the side of the phone, which generated a small electrical current that lit up an indicator on the switchboard. The operator would answer, ask who you wanted to speak to, and then physically connect your line to the other person's line using a patch cord, a short cable with a plug on each end. She would plug one end into your socket and the other into the socket of the person you were calling. Then she would send a ring signal down the line to alert them. When you were done, you would signal again. She would disconnect the cord, and the line would be free for the next call. This worked remarkably well for small exchanges serving a few dozen subscribers. It worked less well as exchanges grew to serve hundreds of subscribers, then thousands. The switchboards became enormous. The number of operators required grew. The physical complexity of routing a call through multiple exchanges. If, say, you wanted to call someone in a different part of the city, or a different city entirely, required the operator to connect to other operators at other boards, each one manually extending the connection. A call that seems instant to us today could require several operators and several minutes to set up. And operators made mistakes. They had good days and bad days. They sometimes connected the wrong lines. They were human, which meant the network was only as reliable and consistent as the humans running it. Someone, eventually, was going to try to remove the human from the equation. Before that happened, though, the phone itself needed to evolve. And one of the most important early evolutions was so basic that it is easy to overlook: figuring out how to signal the exchange without a hand crank. Early telephones used a variety of signaling methods. Some used the crank. Some used a button. Some simply required you to speak loudly into the mouthpiece to trigger a response from the operator. None of these was particularly elegant, and none of them would scale well into an automated system. What was needed was a way for the telephone itself to automatically communicate information to the exchange, not just the fact that you wanted to make a call, but the specific number you wanted to reach. A way for the act of dialing to carry meaning. This required encoding numbers as electrical signals. And to understand how the rotary dial accomplished this, it helps to first understand the electrical environment it was working in. A telephone line, at its most basic, is a loop of copper wire. Current flows out from the telephone exchange, down the line to your telephone, and back up another wire to the exchange. When your phone is on the hook, sitting in its cradle, not in use, this loop is open. No current flows. The exchange can see, by the absence of current, that your phone is idle. When you lift the handset off the cradle, you close the loop. Current begins to flow. The exchange detects this, what engineers call going off hook, and responds by sending a signal back to your phone. A continuous tone that tells you the system is ready to receive your dialing instructions. That tone is dial tone. It is, in the simplest possible terms, the network's way of saying, "I can hear you. Go ahead." Now you have to tell the network which number you want. The rotary dial's answer to this challenge was both ingenious and almost comically simple once you understand it. Rather than trying to encode numbers as complex waveforms or multi-frequency tones, which is what later touch-tone systems would do, the rotary dial encoded numbers as interruptions. Each time you dialed a digit, the dial mechanism briefly opened and closed the electrical circuit a specific number of times. Dial the number 1, and the circuit opened and closed once. Dial the number 5, and it opened and closed 5 times. Dial 0, and it opened and closed 10 times. The exchange, listening carefully to the line, counted these interruptions, these pulses, and used the count to determine which digit you had dialed. This is called pulse dialing. It is, in retrospect, almost charmingly mechanical. You are not sending a sophisticated signal. You are tapping out a number in a code made of nothing more complicated than on and off, on and off. The genius is not in the sophistication of the signal. The genius is in the precision required to make it work reliably, every time, at exactly the right speed. And that precision was the entire engineering challenge of the rotary dial. Pick up a rotary phone and look at the dial. Really look at it. The dial plate, the flat circular disc on the front of the phone, has 10 holes arranged in an arc, each one numbered 0 through 9, with 1 and 2 at the top and 0 at the bottom right. In the center of the plate is a smaller circle, often bearing a number or a letter exchange code, which in the days before all-digit dialing told you which telephone exchange your line belonged to. The holes in the dial plate are finger holes. You insert your index finger into the hole corresponding to the digit you want to dial. Pull the dial clockwise until your finger hits the small metal stop, a curved piece of metal at the right side of the dial plate called the finger stop. And then you release the dial and let it return to its starting position. The release is the important part. The going forward, the clockwise motion, does almost nothing electrically. The dial is designed this way deliberately. It is during the return stroke, the counterclockwise spring-driven return to the starting position, that the pulses are generated. The return speed is controlled by a small mechanism inside the dial body called a governor. The governor is a tiny centrifugal speed regulator. As the dial returns, it drives a small shaft. Connected to that shaft are 2 small weighted arms. Imagine a miniature version of the spinning arms sometimes used to regulate steam engines. As the shaft spins faster, Centrifugal force pushes those arms outward, and as they extend, they engage a friction surface that slows the rotation. The result is a dial that returns at a consistent, controlled speed, regardless of how forcefully it was pulled or how much spring tension remains. This is essential. The telephone exchange is counting pulses, and it is counting them based on timing. Too fast, and the exchange might miscount or miss pulses entirely. Too slow, and the exchange might interpret a single number as two numbers, or simply time out waiting. The speed had to fall within a very narrow window. In the Bell system, the standard was nominally 10 pulses per second, with an acceptable range of roughly 8 to 12. And the governor's job was to keep the dial within that window every single time. Inside the dial mechanism, connected to the return stroke gearing, is the pulse cam, a small disc with a raised lobe that, as it rotates, operates a pair of electrical contacts. Each time the lobe passes the contacts, it opens them briefly. Each opening of the contacts breaks the electrical circuit for a fraction of a second. The exchange detects each break as one pulse. 10 breaks for 0. 1 break for 1. 5 breaks for 5. The contacts themselves are a study in precision. They have to open cleanly. No bouncing, no chatter, no ambiguous partial closures that might confuse the exchange into counting a phantom pulse. They have to close cleanly. They have to do this millions of times over the life of a phone without significant wear. And they have to do it at exactly the right moment in the dial's return cycle, with the governor ensuring the return speed never drifts far enough from specification to cause a miscount. When you consider that all of this was accomplished with nothing more than stamped metal parts, a coiled spring, a governor mechanism borrowed from clockmaking principles, and a pair of electrical contacts, no batteries, no chips, no active electronics of any kind, it becomes difficult not to feel a quiet admiration for the engineers who worked it out. The first practical rotary dial was developed in the early 20th century. AT&T and the Bell system refined it over decades into the mechanism that became standard in North American telephones. The model that most people picture today, the elegant, weighted, satisfyingly heavy dial with its smooth return stroke and authoritative clicking sound, was largely perfected by the 1940s and 1950s and changed very little after that. There was no particular reason to change it. It worked. Now consider the handset, the piece you hold against your ear and mouth. It seems like a simple thing, a handle with an earpiece on one end and a mouthpiece on the other. But inside those two domed cups is the core of what makes telephone communication possible. The mouthpiece contains the transmitter. In the rotary phone era, this was almost universally a carbon microphone, and specifically a carbon granule transmitter. It is one of the oldest practical microphone designs, dating to the 1870s, and it is worth understanding because what it does is almost philosophically satisfying. Inside the transmitter housing, behind the perforated metal face of the mouthpiece, there is a small cup filled with granules of carbon, tiny, irregular particles of compressed carbon roughly the size of coarse sand grains. At the front of this cup is a thin metal diaphragm. When you speak into the mouthpiece, the sound waves from your voice cause variations in air pressure that push against the diaphragm, flexing it back and forth in sync with the sound. As the diaphragm flexes inward, it presses against the carbon granules, compressing them. Compressed carbon conducts electricity more easily than loosely packed carbon. As the diaphragm flexes outward, the granules relax, and their electrical resistance increases. The result is that the electrical current flowing through the transmitter varies in exact proportion to the variations in air pressure caused by your voice. Your voice, in other words, is directly modulating an electrical current. The current that flows out of the transmitter is, in a very real and literal sense, an electrical portrait of your voice. Every nuance, the pitch, the rhythm, the tone, the slight wavering quality that makes your voice recognizably yours, is encoded in the moment-to-moment variations of that current. This current travels down the telephone wire to the exchange, through the switching network, along the line to the person you are calling, and into the earpiece of their handset. And in that earpiece, the receiver, the process runs in reverse. The receiver contains a small electromagnet. The varying current from the transmitter passes through the electromagnet's coil, creating a varying magnetic field. Held against the electromagnet's pole piece is a thin metal diaphragm. As the magnetic field varies with the current, it alternately attracts and relaxes its pull on the diaphragm, causing it to vibrate at exactly the same frequencies as the original sound waves that cause them. The diaphragm's vibrations push against the air inside the earpiece cap, creating variations in air pressure, sound waves, that your ear interprets as your caller's voice. Lift a rotary phone handset. The transmitter in the mouthpiece weighs more than you might expect. The cup of carbon granules has genuine mass. The receiver at the ear end is heavier than its small size suggests. This weight is part of the reason the handset feels substantial and serious, in a way that modern phones do not. There is real mechanism in there, real engineering mass. It also explains something that older users of rotary phones knew without being able to articulate. If you banged the handset on a hard surface, the call quality would often improve temporarily. The impact would jostle the carbon granules, which tended to compact and clump over time, causing the transmitter to become less sensitive. A sharp knock would settle them back into a more uniform distribution, restoring the variable resistance properties they needed to work properly. That is not a design flaw. That is physics. And it is rather endearing that the solution to a problem in an advanced communication technology was, for decades, simply tapping the thing on the table. The housing of the rotary phone, the body of the device itself, deserves more attention than it usually receives. The most iconic rotary phone housing in North American history is the Model 500, designed by Henry Dreyfuss and introduced by Western Electric in 1949. It replaced the earlier Model 302, which had a slightly more upright Art Deco profile, and it remained the standard telephone in American homes for more than 3 decades. Dreyfuss was one of the most significant industrial designers of the 20th century. His work on the Model 500 was not simply aesthetic. He approached the telephone as a human factors problem, meaning he thought carefully about how the object would actually be used by actual human hands in actual human situations. The proportions of the handset were based on detailed measurements of human faces, the distance between the average ear and the average mouth. The handset sits comfortably against the face without requiring you to hold it in a particular way. The receiver cup fits naturally over the ear. The mouthpiece falls naturally near the mouth. The dial is positioned where the index finger naturally rests when the hand is placed on the front of the phone. The finger holes are sized for adult fingers, large enough to insert comfortably, small enough to provide positive registration so you can feel when your finger is properly seated. The finger stop is positioned at a natural limit of a clockwise sweep, so that when your finger reaches it, it does so with a satisfying solidity that tells you, without looking, that the dial is fully wound. The housing itself was injection molded from ABS plastic, a material chosen for its combination of rigidity, impact resistance, and ability to hold sharp detail in molding. Earlier phones had been made from harder, more brittle materials. The Model 302 used a thermosetting plastic that was more heat-resistant, but more prone to cracking. The Model 500's ABS housing could take the ordinary punishment of daily life. Being set down too hard, being dropped, being dragged across desks by its cord. The color palette available for the Model 500 expanded over the years, from the original black to include ivory, beige, pink, aqua, yellow, red, and eventually a range of other colors, in response to consumer demand for telephones that matched kitchen decor. This sounds trivial until you consider what it represents. The telephone had, by the 1950s, become sufficiently embedded in domestic life that people were choosing it with the same aesthetic consideration they gave to appliances and furniture. It was no longer simply a utility device. It was part of the home. The cord connecting the handset to the body of the phone. The coiled cord that stretches when you wander away from the phone and snaps back when you return, became one of the most recognizable design elements of the mid-20th century domestic environment. The coil was not decoration. It was engineering. A straight cord long enough to allow comfortable movement would be inconveniently long when the phone was in use. The coiled cord provided both the reach and the retraction in a compact form. Over time, the cord's inevitable tendency to tangle into a tight, resistant spiral became one of the defining physical experiences of telephone use. The slow untangling of a hopelessly knotted handset cord being a minor universal frustration that most people of a certain age remember with a kind of fond exasperation. There was also a second cord, the line cord connecting the base of the phone to the wall jack. This was typically a flat, two-conductor cord, shorter and less prone to tangling than the handset cord, because it did not move in use. It carried the telephone line itself, the two copper conductors that connected the phone to the local loop, and, through it, to the exchange. Everything about the design of the Model 500, and of the comparable designs produced by telephone manufacturers in Britain, Germany, Sweden, Japan, and elsewhere during the same era, was shaped by two forces simultaneously: the engineering requirements of the telephone system and the human requirements of the people using it. The balance between these two forces produced an object that was, in its quiet way, nearly perfect for its purpose. Nearly perfect. There were a few things it could not do. It could not tell you who was calling before you answered. It had no memory for storing numbers. It could not be used while walking around outside. And dialing a number with many repeated digits, calling a number like 999999, for instance, required patience, because 9 holes required 9 long sweeps of the dial, and you had to wait for the dial to complete its return each time before starting the next digit. These were not design failures. They were simply the boundaries of what the technology could do. And they were accepted because within those boundaries, the telephone worked with a reliability and clarity that continues, honestly, to be underappreciated. When the power goes out in a modern home, the smartphones stop charging. The wireless routers go dark. Voice over internet calling becomes impossible. But in the era of the rotary phone, a power outage had no effect whatsoever on the telephone. It kept working because the telephone did not run on household power. It ran on current supplied directly by the telephone exchange, a carefully regulated 48 volts of direct current flowing continuously down the telephone line. The phone required no battery, no adapter, no power cord into the wall. It drew everything it needed from the line itself. This is why, during disasters and emergencies, the telephone often remained working long after everything else had failed. The exchange had its own backup power. The phone had no household power requirement. The copper wire connecting them was buried underground or strung between poles that could withstand most ordinary storms. The system was, in engineering terms, remarkably fault-tolerant. It is easy now to take that for granted. It is perhaps easier to appreciate it when you notice that the next time a major storm knocks out power to a neighborhood, the people who still have old landline connections can still make calls while everyone else is watching their phone battery percentage tick downward with quiet anxiety. Somewhere in the basement of a telephone exchange building, in the city or town where every rotary phone call eventually arrived, a machine was listening to the pulses coming down the line. That machine, the automatic telephone switch, is the subject of the next part of this story. Because the rotary dial was only half of the system. The dial generated the pulses. But something had to receive those pulses, interpret them, and use them to physically connect your call to the right destination. That something was one of the most extraordinary pieces of mechanical engineering ever built for commercial use. It filled rooms. It weighed tons. It operated in near silence, in climate-controlled buildings, tended by small teams of technicians who spent their careers understanding its moods and maintaining its tolerances. And it worked. For decades, it worked, processing millions of calls a day, routing voices across cities and countries, clicking and stepping through its sequences with a quiet, mechanical determination that the digital systems that replaced it can still, in some ways, only approximate. What it was exactly, how it worked, who invented it, and what remarkable story lies behind its creation is where this documentary goes next. The pulses leave your telephone. They travel as brief interruptions in the electrical current flowing through the copper loop, your phone to the exchange, and back again. Each interruption lasts roughly 60 milliseconds. The gap between interruptions is roughly 40 milliseconds. The exchange equipment at the other end of the line is listening for precisely this pattern, counting each break with a patience and consistency that no human operator could match. But what exactly is doing the counting? To answer that, it helps to understand what the exchange looked like from the outside first, because the building itself was part of the system in a way that modern telecommunications facilities are not. Telephone exchange buildings, particularly those built between the 1920s and the 1960s, were among the most solidly constructed commercial structures in any city. They had to be. The equipment inside them was heavy, sometimes hundreds of tons of switching apparatus, power supplies, and distribution frames packed onto reinforced floors designed to bear loads comparable to those of industrial factories. The buildings were typically windowless on the switching floors, both for security and for climate control. Temperature and humidity had to be kept within tight limits because the mechanical switches inside were precision instruments. Too much humidity could cause corrosion on contacts. Too little could increase static electricity. Temperature swings could cause metal parts to expand and contract enough to affect the tolerances of switches that operated with clearances measured in thousandths of an inch. From the street, these buildings often looked like nothing at all. Solid, utilitarian, sometimes faced in brick or limestone to blend with their neighborhoods, sometimes simply anonymous concrete boxes. Most people walked past them every day without knowing what they were. There was no sign that said, "This is where your phone calls happen." There was no visible activity, no trucks constantly coming and going, just a quiet building humming faintly if you stood close enough to the walls, doing its work in privacy. Inside, though, it was a different world. The main switching room of a large telephone exchange was one of the great industrial interiors of the 20th century. Rows upon rows of metal frames stretched from floor to ceiling, each frame packed with hundreds of small electromechanical switches arranged in orderly banks. The room had a sound, not loud, but constant and unmistakable. A rapid, irregular clicking and chattering, like the sound of 1,000 small insects communicating in code. Each click was a switch stepping through its sequence, responding to pulses from a subscriber's rotary dial, searching for the next available path through the network. The air smelled faintly of machine oil and warm insulation. The lighting was steady and functional, usually fluorescent tubes casting an even, shadowless glow across the ranks of equipment. The floors were raised in some installations, with cables running beneath them. In others, cables descended from overhead trays in thick, neatly dressed bundles, fanning out to individual switch banks with a precision that reflected the telephone company's almost obsessive commitment to orderly wiring. Technicians moved through these rooms with the quiet familiarity of people tending a living system. They knew the sounds. A healthy exchange had a particular rhythm to its clicking. An unhealthy one, a switch sticking, a relay chattering abnormally, a motor running rough, sounded wrong in a way that experienced technicians could detect before any alarm indicator lit up. This was the world that the rotary phone's pulses entered when you dialed a number. And the machine that received them, the automatic switch, was the product of a story that began, improbably, with a funeral director. Almond Brown Strowger was an undertaker in Kansas City, Missouri, in the late 1880s. His business was not going well, and he believed he knew why. The local telephone exchange at the time was operated by human switchboard operators. When someone in Kansas City called and asked to be connected to an undertaker, the operator, a human being with personal relationships, preferences, and, Strowger suspected, financial incentives, was routing those calls to a competing funeral home. Specifically, Strowger believed that one of the operators was the wife of his competitor and was deliberately diverting calls away from his business. Whether or not this suspicion was entirely justified has never been definitively established. What is established is that Strowger, infuriated by his inability to control how his calls were being handled, decided that the solution was to eliminate the human operator entirely. He wanted a system where the caller could connect directly to the desired number without any human intermediary. A system where the switching was done by a machine, responding only to the signals sent by the caller, incapable of favoritism, bribery, eavesdropping, or incompetence. Strowger was not an engineer. He was not an electrician. He was an undertaker. But he had the kind of stubbornness that sometimes produces revolutionary inventions. And in 1891, he was granted United States Patent 447-918 for an automatic telephone exchange. His original model, according to accounts from the period, was built using a round collar box and a set of straight pins. It was crude, but the principle it demonstrated was sound, and it became the foundation for the dominant telephone switching technology of the next 70 years. The Strowger switch, also called the step-by-step switch or the uniselector in some configurations, works on a principle so direct and mechanical that once you understand it, you can almost hear it working. The basic element is a shaft with a wiper arm, a contact arm that can move in 2 dimensions. It can step upward, one position at a time, along a vertical axis, and it can rotate around the shaft. one position at a time, along a horizontal axis. The wiper arm is surrounded by a semicircular bank of contacts arranged in rows and columns, typically 10 rows of 10 contacts each, giving 100 possible positions. When the switch receives pulses from a rotary dial, it steps. One pulse, one step. The first digit you dial causes the switch to step upward by the corresponding number of positions. If you dial a 7, the wiper arm steps up 7 positions, reaching the 7th row. Then the switch pauses, waiting for the next digit. The second digit causes the wiper arm to rotate horizontally by the corresponding number of positions. If you dial a 3, the arm rotates to the third contact in that row. The wiper arm is now resting on one specific contact out of 100. That contact is connected to the line of a specific subscriber or to the input of another switch that handles the next stage of routing. This is the fundamental mechanism. Your finger spins the dial. The dial generates pulses. The pulses travel down the wire. The switch counts them and moves accordingly. Each digit you dial advances the connection one step closer to its destination. For a complete telephone number, say 7 digits, the call would pass through multiple stages of switching, each stage handling 1 or 2 digits. The first switch would use the first digit to select a group. The second switch would use the next digit to narrow the selection within that group, and so on, until the final switch connected the call to the specific line of the person being called. In a large exchange, a single call might pass through 4, 5, or even 6 stages of switching. Each stage involved a separate physical switch, stepping and rotating in response to the digits it received. The entire path from your phone to the destination phone was a chain of mechanical connections, each one established in real time as you dialed, each one a physical piece of metal resting on another physical piece of metal. There were no virtual connections, no software-defined routes, no packets of data finding their way through a network. There was a literal, continuous, unbroken electrical circuit made of copper and contact points, stretching from your handset through the exchange switches to the handset of the person you were calling. Your voice traveled along this circuit as a continuously varying electrical current, and it did so at very nearly the speed of light. When you hung up, the switches released. Springs returned the wiper arms to their resting positions. The contacts opened. The circuit was broken, and the switches were ready for the next call. The elegance of the Stroger system was its directness. Each pulse from the dial produced exactly one mechanical step. There was no interpretation, no processing, no decision-making in any complex sense. The system was purely responsive, cause and effect, repeated across stages, producing a connection. But directness came with limitations. Every active call occupied a dedicated physical path through the switching equipment. A switch engaged by one call could not be used by another call until the first call ended. This meant that the exchange needed enough switches to handle the maximum number of simultaneous calls expected during the busiest hour of the busiest day. If demand exceeded capacity, callers would get a busy signal, not because the person they were calling was on the phone, but because the exchange itself had run out of available switching paths. This problem, how to provision enough equipment to handle peak demand without building so much equipment that most of it sat idle during off-peak hours, became one of the central engineering challenges of 20th century telephony. It was, in a sense, one of the earliest capacity planning problems in the history of technology. and it was addressed through a combination of traffic engineering theory, statistical analysis, and a Danish mathematician named Agner Krarup Erlang. Erlang, working for the Copenhagen Telephone Company in the early 1900s, developed the mathematical models that allowed telephone engineers to calculate how many circuits and switches were needed to provide a given level of service to a given number of subscribers. His unit of measurement, the Erlang, named after him, is still used in telecommunications today. One Erlang represents one circuit continuously occupied for 1 hour. His formulas allowed engineers to predict, with remarkable accuracy, the probability that a caller would encounter a busy condition based on the number of available circuits and the average calling rate of subscribers. This is worth pausing on for a moment, because it represents something genuinely important about the telephone system. The system was not simply engineered in the mechanical sense. It was also engineered statistically. The number of switches in an exchange, the number of trunk lines between exchanges, the capacity of every link in the network, all of it was determined by mathematical models that balanced cost against service quality. Too few circuits, and callers would experience frequent busy signals. Too many, and the telephone company would be paying for equipment that sat unused. The fact that you could, on most occasions, pick up a rotary phone and get a connection to any number you dialed on the first try was not an accident. It was the result of careful statistical engineering, continuously refined based on actual traffic measurements taken at exchanges across the network. The Stroger step-by-step switch dominated telephone switching for the first half of the 20th century. It was manufactured in enormous quantities. It was installed in exchanges from New York to New Zealand. It was reliable, relatively simple to maintain, and well understood by the technicians who tended it. But it had characteristics that, as the telephone network grew, began to cause problems. The clicking of a step-by-step exchange was not merely atmospheric. It was noise, electrical noise as well as acoustic noise. Each time a switch stepped, the making and breaking of contacts generated small electrical transients that could, under certain conditions, be heard as clicks or static on active calls passing through nearby switches. The larger the exchange, the more switches were operating simultaneously, and the greater the cumulative noise. Step-by-step switches also required significant maintenance. The contact surfaces wore over time. The mechanical parts needed lubrication. The springs that returned wiper arms to their home positions could weaken with age. The governors that regulated stepping speed could drift out of adjustment. Each switch was a precision mechanical device, and each one needed periodic attention. Furthermore, the step-by-step architecture was what engineers call a progressive system. Each digit was processed as it was dialed, one stage at a time, in real time. The first digit committed the call to a specific group of switches before the second digit had even been dialed. This meant that routing decisions were made incrementally, without any knowledge of the complete number being dialed. There was no opportunity to look at the full number and choose the most efficient path through the network, because the path was being built digit by digit as the caller dialed. By the 1930s and 1940s, telephone engineers were exploring alternatives. The most significant of these was the crossbar switch. The crossbar switch represented a fundamentally different philosophy of switching. Where the Stroger switch was progressive, building the connection digit by digit, the crossbar system was common control. It received the complete dialed number first, stored it temporarily in a device called a register, and then used a separate piece of equipment called a marker to analyze the number and find the best available path through the switching network. The physical mechanism of the crossbar switch was also different. Instead of a single wiper arm stepping along a bank of contacts, the crossbar switch used a grid of horizontal and vertical bars. At each intersection point, there was a set of contacts. By activating a specific horizontal bar and a specific vertical bar simultaneously, the switch could close the contacts at their intersection, connecting one line to another. The crossbar was faster than the step-by-step switch. It was quieter. It allowed more efficient use of switching paths, because the marker could evaluate the full number and choose the least congested route rather than committing to a path one digit at a time. It generated less electrical noise. And because the common control equipment, the registers and markers, was shared among many calls rather than dedicated to each call individually, the system could handle a higher volume of calls with less total equipment. The first crossbar exchange in the Bell system went into service in Brooklyn, New York in 1938. The technology was gradually deployed across the network over the following decades, coexisting with and eventually replacing Stroger equipment in major metropolitan exchanges. Rural and smaller exchanges often retained their step-by-step equipment for much longer, sometimes into the 1970s and 1980s, because the cost of replacement could not always be justified for areas with lower call volumes. From the caller's perspective, the change from step-by-step to crossbar switching was invisible. You still picked up the phone, heard the dial tone, spun the rotary dial, and waited for the call to connect. The pulses generated by the rotary dial were identical regardless of what type of exchange equipment received them. The system had changed beneath you, and you had no reason to know or care. This is one of the recurring themes in the history of telephone engineering. The system's internal evolution was almost entirely hidden from its users. Billions of dollars were spent. Entire buildings were rewired. Switching technologies were replaced wholesale. And the person making the call noticed nothing, because the interface, the rotary phone on the table, remained the same. The voice itself, once the connection was established, traveled along the telephone line as an analog signal, a continuously varying electrical current that mirrored the continuously varying sound waves of human speech. Understanding what happened to that signal between your mouth and the other person's ear requires understanding a few things about the physics of electrical transmission over copper wire. Copper is an excellent conductor. It offers low resistance to electrical current, which means that a signal can travel a considerable distance along a copper wire without losing too much of its strength. But copper wire is not perfect. Every length of wire has some resistance, and that resistance causes the signal to lose energy, to attenuate, as it travels. The longer the wire, the greater the attenuation. A voice signal that starts out strong at the exchange may arrive at a telephone several miles away significantly weakened. For local calls within the same exchange area, typically covering a radius of a few miles, attenuation was manageable. The wire gauge was chosen to keep signal loss within acceptable limits over the expected distances. Thicker wire has less resistance per unit length, so lines serving distant subscribers used heavier gauge copper. This was an expensive solution, but for local loops, it worked. For longer distances, the problem became more serious. A telephone line stretching across a city, let alone across a state or a continent, would attenuate the signal to the point of inaudibility without some form of amplification. In the early days of telephony, this was a hard limit. Long-distance calling was genuinely difficult, and calls over more than a few dozen miles often suffered from weak, noisy connections that made conversation exhausting. The electrical resistance of the wire absorbed the signal. Interference from nearby power lines, other telephone lines, and atmospheric electrical activity added noise. The ratio of signal to noise, the clarity of the voice compared to the background hiss and crackle, deteriorated with distance. The solution came in stages. The first significant improvement was the loading coil, developed by Michael Pupin and independently by George Campbell around 1900. Loading coils were inductors, coils of wire wound around iron cores, inserted at regular intervals along the telephone line. They worked by compensating for the capacitive effects of the wire, which tended to distort and weaken the signal at voice frequencies. A properly loaded line could carry a voice signal much farther with much less attenuation than an unloaded line. Loading coils were transformative. They extended the practical range of telephone communications significantly. They were installed on lines across the country, typically at intervals of about 6,000 feet, housed in small weatherproof cases mounted on telephone poles or buried in underground vaults. Their presence was invisible to callers, but their absence would have been unmistakable. A world where clear phone calls were only possible within a few miles of the exchange. The second major improvement was the vacuum tube amplifier, and later the transistor amplifier, used in devices called repeaters. A repeater takes a weakened signal, amplifies it back to its original strength, and sends it onward. By placing repeaters at intervals along a long-distance line, the signal could be maintained at usable levels across hundreds or thousands of miles. The first transcontinental telephone line in the United States, completed in 1915, used vacuum tube repeaters to span the distance from New York to San Francisco, roughly 3,400 miles of copper wire. The call that inaugurated the line was placed by Alexander Graham Bell, then 67 years old, from New York to his former assistant Thomas Watson in San Francisco. Bell reportedly said, "Mr. Watson, come here. I want to see you," echoing his famous first telephone call from 1876. Watson, according to the story, replied that it would take him a week this time, given the distance. That call traveled through repeater stations positioned along the route, each one boosting the signal to compensate for the attenuation of the preceding segment. The technology was new, the equipment was expensive, and the call quality, by modern standards, would have been poor. But it worked. A human voice, generated in a room in New York, was heard clearly in a room in San Francisco, transmitted entirely by copper wire and vacuum tubes. This was 1915, a world without commercial radio broadcasting, a world without television, a world in which aviation was barely a decade old, and automobiles were still a novelty in most rural areas. The idea that you could speak to someone 3,000 miles away, in real time, using a device sitting on your desk was not merely impressive. It was, for the people who experienced it for the first time, genuinely astonishing. The carbon microphone transmitter, mentioned earlier, deserves a bit more attention here. because its properties affected the sound quality of every rotary phone call in a way that people who grew up with the technology remember viscerally, even if they cannot explain why. The carbon transmitter had a frequency response that was deliberately limited. It was designed to transmit the range of frequencies most important for speech intelligibility, roughly 300 to 3,400 Hz, and to attenuate frequencies outside that range. This was not a limitation imposed by the carbon granules themselves, though they did have natural frequency response characteristics. It was a design choice enforced by the overall telephone circuit, intended to minimize bandwidth usage on the network. Bandwidth, in the analog telephone world, was a physical resource. Each voice call occupied a specific range of frequencies on the wire. The narrower that range, the more calls could be carried on a single cable using a technique called frequency division multiplexing, where multiple calls were shifted to different frequency bands and transmitted simultaneously on the same physical wire. Limiting each call to the 300 to 3,400 Hz band was a compromise between intelligibility and capacity. The result was a sound that was perfectly adequate for understanding speech, but that stripped away certain qualities of the human voice. The deep resonance of a bass voice was slightly thinned. The sibilant clarity of certain consonants was slightly softened. The overall effect was a voice that sounded recognizably like the speaker, but slightly compressed, slightly flattened, as if heard through a particular kind of distance that was not quite spatial. Anyone who remembers making calls on a rotary phone remembers that sound. It was warm but narrow, clear but constrained, intimate in a way that modern digital phone calls, with their wider frequency response and occasional compression artifacts, sometimes are not. The carbon microphone gave voices a quality that was specific to the telephone, a telephone voice. And for decades, that quality was simply what a phone call sounded like. There were also quirks of the carbon transmitter that became part of the experience. Over time, the carbon granules would compact, reducing the transmitter's sensitivity and making the caller's voice sound quieter to the person on the other end. The solution, as noted earlier, was often physical, tapping the handset against a surface to redistribute the granules. More thorough maintenance involved opening the transmitter cup and replacing the granules entirely, a task that telephone company technicians performed as part of routine service. The receiver in the earpiece, meanwhile, was a more stable device. It used a permanent magnet and an electromagnet working together to drive a metal diaphragm. And its construction was robust enough that receivers could last for decades without significant degradation. The sound they produced was characteristically clear in the mid-range and somewhat limited at the frequency extremes, matching the bandwidth of the overall telephone circuit. Together, the transmitter and receiver defined the acoustic experience of the telephone for most of the 20th century. They were not high-fidelity devices. They were not designed to be. They were designed to carry human speech intelligibly and efficiently across a network of limited bandwidth. And at that specific task, they were remarkably good. The ringer mechanism in a rotary phone, the device that made the phone ring when someone called you, operated on a completely different electrical principle than the rest of the phone. During a call, the telephone line carried direct current, a steady flow of electrons in one direction, supplied by the exchange's battery. The voice signal was superimposed on this direct current as small variations. But the ring signal was alternating current, a current that reversed direction many times per second, at a frequency of roughly 20 Hz and a voltage of roughly 90 volts. This is worth emphasizing. 90 volts. The ringing signal sent down the telephone line to make your phone ring was a genuinely significant electrical signal, far stronger than the 48-volt DC current used during a call, and more than sufficient to deliver a noticeable shock to anyone who happened to be touching bare wire connections when a call came in. Telephone technicians learned early in their careers to treat ringing lines with respect. Inside the phone, the ringer consisted of two small electromagnetic coils, a metal striker called a clapper, and two metal bells, the classic hemispherical gongs that produce the familiar two-tone ring. The alternating current of the ring signal passed through the coils, creating an alternating magnetic field that pulled the clapper back and forth between the two bells. Each half cycle of the AC signal pulled the clapper toward one bell, then the other, producing the distinctive ringing sound. The ring pattern, the cadence of ringing and silence, was controlled by the exchange, not by the phone. In the United States, the standard ring pattern was 2 seconds of ringing, followed by 4 seconds of silence, repeated until the call was answered or the caller hung up. This pattern was recognizable and consistent across the entire network, a small but significant element of the shared cultural experience of telephone use. On party lines, shared telephone lines serving multiple subscribers, common in rural areas where the cost of individual lines was prohibitive, different ring patterns were used to indicate which subscriber the call was for. Your phone and your neighbor's phone might share the same physical line, but your ring pattern would be 2 short rings, while your neighbor's would be 1 long ring. You were expected to answer only your own pattern and to refrain from picking up during someone else's ring. In practice, of course, eavesdropping on party lines was a widespread and well-known phenomenon, a source of both community gossip and considerable annoyance. The ringer's design had one additional clever feature. It included a capacitor, an electrical component that blocks direct current but allows alternating current to pass, wired in series with the ringer coils. This meant that the ringer was electrically invisible during a normal call. The direct current flowing during conversation could not pass through the capacitor, so it could not energize the ringer coils. Only the alternating current of the ring signal could reach the ringer, ensuring that the bells rang only when they were supposed to. This is a small detail, but it is representative of the kind of thoughtful circuit design that characterized the rotary telephone. Every component had a specific purpose, and the interactions between components were carefully managed to prevent unwanted behavior. The phone was, in engineering terms, a well-integrated system in which nothing was wasted and nothing was left to chance. The next time you see a rotary phone, in a museum, in an antique shop, in a photograph, consider for a moment the chain of events that occurred each time someone used it. You lift the handset. The hook switch closes. Current flows. The exchange detects the current and sends dial tone. You insert your finger into a hole on the dial. You pull the dial clockwise to the finger stop. You release it. The governor controls the return speed. The pulse cam opens and closes the circuit a precise number of times. The exchange counts the pulses and steps a switch. You repeat this for each digit. Each digit steps another switch. The switches chain together, building a path through the network. The final switch in the chain connects to the line of the person you are calling. The exchange sends a 90-volt alternating current ring signal down that line. The capacitor in their phone allows the ring signal through. The ringer coils energize. The clapper swings. The bells ring. They pick up. Their hook switch closes. Current flows on their end. The exchange detects this and stops the ring signal. A circuit now exists, unbroken, from your transmitter through the switching network to their receiver, and from their transmitter back through the network to your receiver. You speak. Carbon granules compress and release. Current varies. The variations travel through copper wire, through switch contacts, through more copper wire. At the other end, an electromagnet and a diaphragm convert the current back into sound. Two people in two different rooms, in two different parts of a city or a country, talking to each other as if they were in the same room. All of it accomplished with copper, carbon, springs, magnets, and the careful counting of pulses generated by a spinning dial. No software, no microprocessor, no internet protocol, no satellite, just physics carefully arranged. The system that made all of this possible, the network of wires, the exchanges, the operators who preceded the machines, the engineers who built and maintained it all, is the subject of the next part of this story. Because the rotary phone, for all its cleverness, was only the endpoint. The real story is the network it was connected to, and the people who built it. Step outside for a moment. Look up. In many neighborhoods, especially older ones, you can still see them, wooden poles, darkened with age and creosote, standing along the edges of roads in lines that run toward the horizon. Some of them still carry wires. Many of them carry fewer wires now than they once did. A few stand with nothing on them at all, left in place because removing them would cost more than ignoring them. Those poles were the skeleton of the telephone network. And the wires they carried, pairs of copper conductors, twisted together and strung between insulators, were the network's nervous system. Every call that traveled through a rotary phone began and ended on copper wire. And the sheer physical scale of the network that was built to carry those calls remains, even now, difficult to fully comprehend. By the middle of the 20th century, the Bell system alone, the network operated by AT&T and its subsidiaries in the United States, maintained more than 100 million miles of copper wire, not 100 million miles of cable, 100 million miles of individual wire, twisted into pairs, bundled into cables, strung on poles, buried in conduits, run along the walls of buildings, and terminated on millions of individual telephone sets in homes, offices, hospitals, factories, and farms. This infrastructure was not built all at once. It grew, year by year, pole by pole, trench by trench, over roughly 8 decades. And the story of how it was built is a story about labor, logistics, geography, weather, and the peculiar challenge of connecting every building in a country to a single unified network. The basic unit of the telephone network's physical plant was the local loop. the pair of copper wires connecting an individual telephone to the nearest telephone exchange. Every subscriber had a dedicated local loop: your phone, your pair of wires, your connection to the exchange. Nobody else shared that pair unless you were on a party line, and even then, the physical wire was shared only with a handful of other subscribers. The local loop began at the subscriber's premises, at the telephone jack on the wall, which was itself connected by wire run through the walls or along the baseboards to an interface point on the outside of the building. From there, the wire ran to the nearest telephone pole or underground access point and joined a cable containing many other pairs, all running together toward the exchange. These cables grew thicker as they got closer to the exchange because they were collecting more and more subscriber pairs from more and more neighborhoods. A cable leaving a residential street might contain 25 pairs. By the time it reached a main distribution route, it might contain hundreds or even thousands of pairs, bundled together in a cable as thick as a man's arm. At the exchange building, the cables entered through underground conduits and terminated on a massive piece of equipment called the main distribution frame, a towering rack of connection points, usually stretching across an entire wall, where every subscriber's pair was connected to the switching equipment inside the exchange. The main distribution frame was both an organizational tool and a protection point. It allowed technicians to connect, disconnect, test, and rearrange subscriber lines without disturbing the switching equipment. It also contained protection devices, small fuses, and gas discharge tubes designed to prevent damage to the exchange equipment in the event that a lightning strike or a power line contact sent a high-voltage surge down a telephone line. The technicians who maintained the main distribution frame were specialists. Their work required a meticulous understanding of the cable network's numbering system, because any given pair of wires in any given cable had to be traceable from the subscriber's premises, through the outside plant, through the cable entrance facility, and onto the frame, where it was cross-connected to the correct switching equipment. A mistake, a misidentified pair, a cross-connection made to the wrong terminal could knock out someone's phone service or, worse, connect them to the wrong line entirely. The precision of this work is easy to underestimate. The Bell System's cable records, detailed maps and logs documenting every cable, every pair, every splice, every cross-connection, filled warehouses. They were maintained by hand for most of the network's history, updated by technicians after every installation, repair, and modification. Keeping these records accurate was essential, because without them, troubleshooting a problem on any single pair of wires out of millions became a near impossible task. The outside plant, the cables, poles, conduits, and hardware that made up the physical network between the exchange and the subscriber, was exposed to the world in a way that the switching equipment inside the exchange was not. Telephone poles had to withstand wind, ice, rot, woodpecker damage, automobile collisions, and the weight of the wires they carried. The poles themselves were typically made from southern yellow pine or western red cedar, treated with creosote or penachlorophenol to resist decay and insect damage. A well-treated pole could last 40 years or more. An untreated pole in a wet climate might fail in less than 10. The wires strung between poles were initially bare copper, exposed to the elements. Bare wire worked adequately for single pairs. But as the network grew and more wires were strung on the same poles, the risk of contact between adjacent wires, causing crosstalk, where you could faintly hear someone else's conversation on your line, increased. The solution was to twist each pair of wires around each other at regular intervals. The twisting canceled out much of the electromagnetic interference between adjacent pairs, reducing crosstalk to acceptable levels. This is why telephone cable is called twisted pair cable, and it is a principle that persists in modern networking cables to this day. As the network expanded and subscriber density increased, individual open-wire pairs on poles gave way to bundled cables, many pairs enclosed in a common sheath of lead, and later polyethylene for protection. These cables could be strung on poles using a steel messenger wire for support, or they could be pulled through underground conduit systems built beneath city streets. Underground construction was more expensive than aerial construction, but it was more durable, less susceptible to storm damage, and less visually intrusive. In dense urban areas, underground cable became standard. Cities developed extensive networks of conduit, small tunnels, usually made of clay tile or later PVC pipe, running beneath sidewalks and streets, through which cables were pulled by hand or by motorized winch. The engineering of these conduit systems was unglamorous but critical. Conduits had to be deep enough to avoid being disturbed by road construction or utility work, but shallow enough to be accessible for maintenance. They had to slope correctly to allow drainage. Water infiltration was a constant enemy of cable integrity. They had to be large enough to accommodate not just the current cables, but future cables, because adding new conduit in a dense urban area was vastly more expensive than pulling a new cable through existing conduit. Manholes, underground chambers located at intervals along the conduit route, provided access points where technicians could enter to splice cables, reroute pairs, and perform repairs. A telephone manhole was a small underground room, typically large enough for 1 or 2 people to work in, fitted with cable racks, splice cases, and sometimes temporary lighting and ventilation. The work done in these spaces was skilled, physical, and frequently unpleasant, dark, damp, and confined. In winter, manholes filled with cold water. In summer, they were hot and poorly ventilated. The technicians who worked in them were among the least visible and most essential members of the telephone company's workforce. Splicing, the process of connecting individual wire pairs within a cable, was a task that demanded extraordinary manual precision. A cable containing, say, 600 pairs consisted of 1,200 individual conductors, each one color-coded according to a standardized scheme that identified its pair and its position within the cable. A splicer had to identify each conductor by its color code, match it to the corresponding conductor in the adjacent cable, and join them together using a small hand tool that twisted the bare copper ends tightly, which was then insulated with a small sleeve. A single splice case, the protective enclosure around a set of spliced pairs, might contain hundreds of individual splices, each one handmade, each one critical to the proper functioning of a subscriber's telephone service. A poorly made splice could cause noise, intermittent service, or complete failure on the affected pair. A misidentified pair could connect the wrong subscriber to the wrong line. The Bell System's splicers were trained rigorously. The work was repetitive and demanded sustained concentration. It was also, in its own way, a craft. Experienced splicers took pride in the neatness and reliability of their work, and a well-made splice case, opened years later for maintenance, could be immediately identified as the work of a skilled technician by the orderliness of the conductor layout and the tightness of the splices. If the copper wire was the network's nervous system, the telephone operators who preceded, and for decades coexisted with, the automatic switching equipment were its brain. And their story is one of the most human chapters in the history of telecommunications. The first telephone operators were boys. Teenage boys, hired in the late 1870s and early 1880s to sit at switchboards in the earliest exchanges, connecting calls by plugging patch cords into jacks. This arrangement did not last long. The boys were, by most accounts, rude, impatient, and prone to pranks. They argued with callers, they disconnected calls deliberately. They were, in short, teenagers. By the mid-1880s, telephone companies had almost universally replaced male operators with young women, and the telephone operator became one of the most recognizable female occupations of the late 19th and early 20th centuries. The women hired for the job were typically between the ages of 17 and 26. Unmarried. Married women were not hired by most telephone companies until much later, with clear voices, calm temperaments, and good hearing. They were expected to be polite under all circumstances, fast, accurate, and emotionally steady. The work was demanding in ways that are difficult to appreciate without seeing a working switchboard. The operator sat before a vertical panel fitted with rows of jacks, one for each subscriber line served by the exchange, and a set of cord pairs at her position. Each cord pair consisted of a front cord and a rear cord, each terminated with a plug, connected together through the operator's position equipment. When a subscriber lifted their handset, a small lamp lit up on the switchboard. The line lamp, powered by the current flowing through the subscriber's loop. The operator would insert the rear plug of a cord pair into the subscriber's jack and say, "Number please," or, in some exchanges, simply, "Yes," or "Operator." The subscriber would give the desired number. The operator would then insert the front plug into the jack of the called party and ring the line by pressing a ringing key. If the called party answered, the operator would split the connection, electrically joining the two subscribers through the cord pair, and move on to the next waiting call. Her line lamp would extinguish, replaced by a supervisory lamp that would light up again when either party hung up, signaling the operator to take down the connection and free the cord pair for the next call. A busy operator at a large exchange might handle hundreds of calls per hour. She had to remember number formats, exchange boundaries, routing procedures for calls destined for other exchanges, and the protocols for special services, emergency calls, collect calls, person-to-person calls, time announcements. She had to do all of this while wearing a headset that delivered a constant stream of voices into her ear, sitting in a posture that modern ergonomics would consider unhealthy, for shifts that commonly lasted 8 hours. The physical environment of a large switchboard room was striking. Dozens or even hundreds of operators sat side by side at a long switchboard, their arms in constant motion, reaching, plugging, unplugging, pressing keys, writing notes. Supervisors walked behind the rows, monitoring performance, timing call setup speeds, and intervening when problems arose. The room hummed with the low murmur of hundreds of simultaneous conversations, punctuated by the clicking of keys and the quiet voices of operators repeating numbers and giving instructions. Discipline was strict. Operators were expected to use standardized phrases. Personal conversation was forbidden. Chewing gum was forbidden. Unnecessary movement was discouraged. Breaks were scheduled and monitored. The telephone company expected its operators to function with the consistency and reliability of machines. And the irony of this expectation, that the very qualities being demanded of these women were the qualities that would eventually make them replaceable by actual machines, was not lost on everyone, even at the time. The operators' union, where it existed, fought for better working conditions, shorter shifts, and fair wages. In many cities, telephone operators went on strike at various points during the early 20th century, disrupting service and drawing public attention to the demanding nature of their work. The relationship between the telephone companies and their operators was complex. The companies depended on them utterly, advertised their courtesy and efficiency as selling points, and simultaneously worked to develop the automatic switching technology that would make them unnecessary. By the 1920s and 1930s, automatic switching had begun to replace operators for local calls in many exchanges. The rotary dial, which allowed subscribers to directly generate the signals needed by automatic switches, was the instrument of this transition. But operators were not eliminated overnight. Long-distance calls, in particular, continued to require operator assistance well into the 1950s and beyond. International calls required operators even longer. And certain services, directory assistance, emergency services, collect calls, retained human operators for decades after local dialing had been fully automated. The last manual switchboard in the Bell system was decommissioned in 1978 in a small town called Bryant Pond, Maine. Though it is worth noting that this date is sometimes disputed depending on how one defines the boundaries of the Bell system. Regardless, by the late 20th century, the telephone operator had largely disappeared from the daily experience of making a call, surviving mainly in specialized roles and in the cultural memory of an older generation. Their contribution was enormous. For roughly 7 decades, these women, and they were overwhelmingly women, were the telephone network. Every call passed through their hands. They were the intelligence that routed the system before machines could do it. And they did it with a speed and accuracy that, given the tools available to them, was genuinely extraordinary. The automatic switch that replaced the operators, the Stroger step-by-step system, and later the crossbar system, was discussed in the previous section. But there is a deeper story behind the Stroger invention that is worth returning to, because it illustrates something important about how technological change happens. Almon Stroger's patent was granted in 1891. His first commercial installation was in LaPorte, Indiana, in 1892. The system worked, but it was rough. Early automatic exchanges were noisy, unreliable compared to well-run manual boards, and expensive to install. Stroger himself was not a gifted businessman, and he eventually sold his interests in the Stroger Automatic Telephone Exchange Company. The company continued without him, refining the technology and licensing it to telephone companies around the world. The Bell system, the dominant telephone carrier in the United States, was initially skeptical of automatic switching. The company had invested heavily in manual switchboard technology and employed tens of thousands of operators. The transition to automatic switching would require enormous capital expenditure and would render much of the existing equipment and workforce obsolete. There was also a genuine belief within parts of the company that human operators provided a higher quality of service than machines, that the personal touch of an operator who knew her subscribers' names, who could handle unusual requests, who could exercise judgment in ambiguous situations, was a competitive advantage worth preserving. This debate continued within the Bell system for years. The arguments in favor of automation were primarily economic. Operators' wages were the single largest operating expense of a telephone exchange, and as the network grew, the number of operators required grew faster than the subscriber base, because the complexity of routing calls through a large network increased geometrically with the number of subscribers. There was a mathematical ceiling beyond which manual switching simply could not scale. The Bell system eventually embraced automation, developing its own versions of automatic switching equipment, the panel switch, used primarily in large cities in the 1920s and 1930s, and later the crossbar switch. The company's approach was characteristically methodical. Rather than deploying automatic switching rapidly and accepting a period of reduced service quality, the Bell system transitioned gradually, exchange by exchange, area by area, over decades. Manual and automatic equipment coexisted in the same exchanges during the transition period, with operators handling calls that the automatic equipment could not yet process. This gradualism was expensive but effective. The service quality experienced by subscribers remained high throughout the transition. Most callers were unaware of whether their call was being processed by human operators or automatic switches, and the telephone company preferred it that way. The transition was, from the subscriber's perspective, nearly invisible. Long-distance calling presented challenges that local automatic switching could not address. And the story of how long-distance service evolved is a story of both engineering and economics. In the early decades of telephony, a long-distance call was an event. You did not casually pick up the phone and call someone in another state. You planned the call. You might schedule it in advance through the operator. You knew it would be expensive. Long-distance rates were, for most of the telephone's history, significantly higher than local rates, reflecting both the higher cost of the infrastructure required and the limited capacity of the long-distance network. A long-distance call in, say, 1930, worked like this. You would pick up your phone and tell your local operator that you wanted to place a long-distance call. Your local operator would contact a long-distance operator, often located in a separate, specialized long-distance switchboard room, and give her the destination number. The long-distance operator would then establish a connection through a series of toll switches and trunk lines, possibly involving operators at intermediate points along the route. Trunk lines, high-capacity circuits connecting one exchange to another or one city to another, were the long-distance network's arteries. They were expensive to build because they required heavy-gauge copper wire, loading coils, repeater amplifiers, and in many cases, dedicated right-of-way for the pole lines or conduit systems that carried them. The number of trunk circuits between any two cities was limited, and during peak hours, business mornings, holiday afternoons, all available trunks between popular destinations might be fully occupied, forcing callers to wait or try again later. The economics of long-distance service drove a relentless search for ways to carry more calls on less wire. Frequency division multiplexing, mentioned earlier, allowed multiple voice channels to share a single pair of wires by shifting each call to a different frequency band. A system called the Type K carrier, introduced by the Bell system in the 1930s, could carry 12 simultaneous calls on a single pair of wires. Later systems increased this capacity dramatically. The L-carrier coaxial cable systems introduced in the 1940s and 1950s could carry thousands of simultaneous calls on a single coaxial tube. The introduction of direct distance dialing, the ability for a subscriber to place a long-distance call by dialing the full number, including area code, without operator assistance, began in the early 1950s. The first customer-dialed long-distance call in the Bell system was made on November 10, 1918. From Englewood, New Jersey, to Alameda, California. The mayor of Englewood dialed the 11-digit number, 1, plus the area code, plus the 7-digit local number, and the call was routed automatically through the toll switching network. This was a landmark event in the history of telecommunications, though it received relatively modest public attention at the time. The technology that made it possible, the ability of the toll switching network to interpret a dialed area code and route the call to the correct distant exchange without human intervention, was the product of decades of engineering development. The area code system itself, formerly known as the North American Numbering Plan, had been designed and implemented by AT&T engineers in the late 1940s, dividing the United States and Canada into numbering plan areas, each identified by a 3-digit code. The numbering plan was designed with the rotary dial in mind. Area codes were assigned based partly on population and call volume, with the most frequently called areas receiving codes that were fastest to dial. New York City received area code 212, a total of only 5 pulses on a rotary dial, while sparsely populated areas received codes with higher digits, requiring more pulses and more time. This was a deliberate optimization. In a system where every digit dialed took a measurable amount of time, roughly a second per digit for higher numbers, reducing the dialing time for the most common destinations saved millions of cumulative hours of network holding time and switching equipment engagement. There is something quietly remarkable about this. The numbering system that organized telephone service for an entire continent was designed, in part, around the mechanical characteristics of a small spring-driven dial on the front of a telephone. The physical properties of the interface shape the architecture of the network. The tail, in a sense, wagged the dog. Throughout this entire era, from the first crude automatic exchanges of the 1890s to the continent-spanning direct distance dialing network of the 1960s, the rotary phone sat on the table, unchanged in its essential function. The housing colors changed. The handset shape evolved slightly. The cord material improved. The internal components were refined. But the fundamental interaction, lift the handset, hear the tone, spin the dial, wait for the connection, remained the same for the better part of 70 years. There is a word for an interface that remains stable while the system behind it undergoes continuous, radical transformation. The word is mature. The rotary phone was a mature interface. It asked nothing of the user that was difficult to learn, nothing that was difficult to remember. nothing that varied from one phone to another, or one decade to another. A person who learned to use a rotary phone in 1935 could use any rotary phone in 1975 without instruction. The dial was the same. The procedure was the same. The handset fit the same hand and the same face. This stability was not accidental. It was a design principle. The Bell system understood that the telephone was a universal service, used by children and elderly people, by literate and illiterate people, by people who were comfortable with technology and people who were intimidated by it. The interface had to be so simple, so consistent, and so forgiving that virtually anyone could use it successfully without training. The rotary dial met this standard. It provided physical guidance. The finger holes told you where to put your finger. The finger stop told you when to stop. The spring-driven return did the work for you. It provided auditory feedback. The clicking of the dial's return stroke confirmed that the mechanism was working. It was resistant to user error. If you dialed a wrong digit, you simply hung up and started over. There was no complex error recovery procedure, no confusing menu, no ambiguous state. The phone was either on the hook or off the hook, and the dial either worked or it did not. In an era increasingly preoccupied with user experience design and interface optimization, it is worth reflecting on the rotary phone's interface as an example of something that was, within its constraints, almost optimally designed. Not because it was fast, it was not. Not because it was versatile, it was not. But because it was learnable, consistent, forgiving, and reliable, which for a universal service tool may be the qualities that matter most. The constraints were real, though. Dialing was slow. A 7-digit number dialed on a rotary phone took, depending on the digits, roughly 7 to 10 seconds. A long-distance number with area code took longer. A person making many calls in succession, a business user, a switchboard operator, would find the cumulative dialing time significant. And as the telephone network grew more sophisticated, as new services were introduced that required the subscriber to send signals to the network during a call, not just at the beginning, the rotary dial's pulse-based signaling method became a limitation. Pulse dialing could only send digits. It could not easily send the kinds of complex, multifunction signals that newer services would require. The solution, tone-based dialing, using a keypad instead of a rotary dial, was already being developed. Its introduction would eventually end the rotary phone's reign as the standard telephone interface. But that transition, and the engineering behind it, belongs to the final section of this story. For now, it is enough to say that the rotary phone, the copper wire, the carbon microphone, the Stroger switch, the crossbar exchange, the operator at her switchboard, the splicer in the manhole, the loading coil on the pole, the repeater on the long-distance line, all of these, together, constituted a system of almost unbelievable complexity and coordination, built and maintained by hundreds of thousands of people over the better part of a century, serving hundreds of millions of subscribers, carrying billions of conversations. And at its center, at the point where all of that infrastructure met the human being it was built to serve, there was a small, heavy, elegantly designed object on a table, with a dial on the front and a handset on the top, waiting quietly for someone to pick it up. By the early 1960s, The rotary telephone had reached a kind of quiet zenith. There were more than 80 million telephones in service in the United States alone. Virtually every household with electricity had one. Many had two. Businesses had dozens. The telephone had ceased to be a novelty or a luxury, and had become something closer to a utility, as essential and as unremarkable as running water or electric light. The network behind those telephones had grown into the largest and most complex machine ever built by human beings. This is not hyperbole. Engineers and historians who studied the Bell system in its mature form described it in precisely those terms. The telephone network was a single, interconnected, continuously operating machine that spanned a continent, comprised billions of individual components, served hundreds of millions of users simultaneously, and operated with a reliability that most people never had occasion to question. The reliability numbers were extraordinary. The Bell system's engineering target for dial tone, the time between lifting the handset and hearing the tone that signaled the network was ready, was less than 3 seconds, achieved 99% of the time. The target for call completion, the probability that a properly dialed call would reach the intended destination, was above 98% for local calls and above 95% for long-distance calls. These numbers were not aspirational. They were measured, reported, and enforced. Exchanges that fell below standard were identified and corrected. Equipment that caused failures was replaced. The entire system operated under a culture of engineering discipline that bordered, at times, on the obsessive. And all of it depended, at the subscriber end, on a device with no battery, no active electronics, and a user interface consisting of a spring-loaded dial with 10 holes in it. The scale of deployment was matched by the scale of manufacturing. Western Electric, the Bell System's manufacturing subsidiary, produced rotary telephones in quantities that rivaled the automobile industry. The Hawthorne Works in Cicero, Illinois, Western Electric's main manufacturing plant, was at one point the largest industrial complex in the world, employing over 45,000 workers. Telephones, switching equipment, cable, and the thousands of other components required by the network flowed out of this facility and others like it in a continuous stream, year after year, decade after decade. The Model 500 telephone alone was produced in the tens of millions. Each one was assembled from hundreds of individual parts, molded plastic housings, stamped metal brackets, precision-wound coils, carefully graded carbon granules, spring steel contact sets, handset cords, line cords, dial mechanisms with their governors and pulse cams, and return springs. Each part was manufactured to specification, inspected, and assembled by workers who repeated the same operations thousands of times a day. The quality control was rigorous. Every telephone was tested before it left the factory. The dial was tested for pulse rate and ratio. The transmitter was tested for sensitivity and frequency response. The receiver was tested for output. The ringer was tested for loudness and tone. The hook switch was tested for electrical continuity. A telephone that failed any test was rejected, repaired, and retested. This might seem excessive for a device that most people regarded as a simple household object. But the telephone company understood something that the subscriber did not. Every telephone was a component of the network. A malfunctioning telephone did not merely inconvenience its owner. It could generate false signals that confused exchange equipment, cause noise on shared cable pairs that degraded service for other subscribers, or fail to properly transmit or receive ringing signals, leading to missed calls. The network could tolerate a certain number of defective endpoints. But beyond that tolerance, service quality for everyone began to degrade. Quality control at the manufacturing stage was, in a very real sense, network maintenance performed in advance. The Bell System's approach to telephone deployment was also distinctive. In most of the United States, subscribers did not buy their telephones. They leased them from the telephone company as part of their monthly service. The telephone remained the property of AT&T. If it malfunctioned, the telephone company replaced it at no charge. If the subscriber moved, the telephone stayed with the premises or was returned to the company for refurbishment and redeployment. This leasing model had several consequences. It meant that the telephone company controlled the quality of every device connected to its network, preventing subscribers from attaching poorly made or incompatible equipment that might cause problems. It meant that telephones were designed for extreme durability, because the company bore the cost of replacement. A phone that lasted 30 years was far more economical than one that lasted 5. And it meant that the telephone, as a consumer object, occupied an unusual category. It was a device that almost everyone used, that sat in almost every home, but that almost no one actually owned. This changed in 1984, when the breakup of the Bell System, the result of a landmark antitrust case brought by the United States Department of Justice, separated AT&T's long-distance operations from the local telephone companies and opened the market for telephone equipment to competition. After 1984, subscribers could buy their own telephones from any manufacturer and connect them to the network, provided the equipment met basic technical standards. The era of the leased, company-owned telephone was over. By that time, though, the rotary phone itself was already in decline. The technology that displaced the rotary dial was not new. It had been under development at Bell Laboratories since the 1940s, and it had been available to subscribers on a limited basis since the early 1960s. It was called touch tone, and it used a completely different method of signaling. Instead of generating pulses by opening and closing the line circuit, the touch tone keypad generated tones, specifically pairs of tones, one from a group of 4 low frequencies and one from a group of 3 high frequencies, combined to produce a unique dual-tone signal for each of the 12 keys on the pad. This system was called dual-tone multi-frequency signaling, or DTMF. When you pressed a key on a touch-tone phone, the phone generated 2 simultaneous audio tones that were transmitted down the line to the exchange. The exchange equipment detected the tones, identified the corresponding digit, and processed it. The entire transaction, pressing the key, generating the tones, detecting and decoding them at the exchange, took a fraction of a second. By comparison, dialing a single digit on a rotary phone required, depending on the digit, up to approximately 1 second for the dial's return stroke, plus the time required to insert the finger, pull the dial to the stop, and release it. The speed advantage was significant. Dialing a 7-digit number on a touch-tone phone took roughly 3 to 4 seconds. Dialing the same number on a rotary phone took 7 to 10 seconds. for a single call, the difference was minor. For a network handling hundreds of millions of calls per day, the cumulative difference in switching equipment holding time was substantial. Every second that exchange equipment spent waiting for a subscriber to finish dialing was a second that equipment could not be used to process another call. Faster dialing meant more efficient use of the network, but speed was only part of the advantage. The more profound change was that DTMF tones could be sent at any time during a call, not just at the beginning. This capability, called end-to-end signaling, opened the door to a new category of telephone services that the rotary dial simply could not support. With DTMF, a caller could interact with automated systems by pressing keys in response to recorded prompts. This made possible automated banking by phone, voicemail systems, interactive voice response systems, and eventually the elaborate menu trees that became a ubiquitous and frequently frustrating feature of modern customer service. None of these services could have existed in a purely rotary dial world, because the rotary dial could only send signals when the line was in the dialing state, before the call was connected. Once the call was established, the rotary dial had no way to send additional information. Touch-tone service was introduced to the public at the 1962 World's Fair in Seattle. The first commercial touch-tone service was offered in Carnegie and Greensburg, Pennsylvania, on November 18, 1963. The new phones were initially offered as a premium service, with a small monthly surcharge for the touch-tone line, because the exchange equipment required to process DTMF signals was an additional cost. Many subscribers, seeing no particular reason to pay extra for faster dialing, kept their rotary phones. The transition was gradual. Throughout the 1960s and 1970s, rotary and touch-tone phones coexisted on the same network. The exchange equipment was designed to accept both pulse and DTMF signals, so subscribers could choose either type of phone without affecting their ability to make calls. The rotary phone continued to work exactly as it always had. Nothing was taken away from the subscriber who preferred the old technology. But the trend was clear. New telephone installations increasingly used touch-tone by default. Businesses adopted touch-tone almost universally because the speed and flexibility advantages were immediately practical. Younger subscribers, who had no particular attachment to the rotary dial, chose touch-tone when given the option. The rotary phone's share of the installed base declined year by year, slowly but steadily. By the 1980s, touch-tone had become the dominant signaling method in most developed countries. By the 1990s, the rotary phone had become a relic, still functional, still supported by the network in most areas, but no longer manufactured in significant quantities and no longer the default choice for new subscribers. The last major telephone company to discontinue support for pulse dialing on its network did so in the early 2000s, though the exact date varies by country and carrier. In some rural areas, rotary phones continued to work on the public switch telephone network well into the 21st century, quietly pulsing out their digits into exchanges that were, by that point, fully digital and merely emulating the electromechanical behavior of switches that had been decommissioned decades earlier. There is something poignant about that. A digital switch, built with microprocessors and software, counting simulated pulses from a device invented in the 1890s, maintaining backward compatibility with a technology that predated the computer by half a century. The network had been rebuilt entirely, copper replaced by fiber optics in the backbone, analog switches replaced by digital switches, Digital switches replaced by packet-switched voice over Internet protocol, but the rotary phone, stubborn and unchanging, could still make a call. The engineering philosophy that produced the rotary telephone is worth examining, because it is fundamentally different from the philosophy that produces modern consumer electronics. Modern devices are designed with an expected lifespan measured in years, typically 2 to 5 years for a smartphone, perhaps a decade for a well-made appliance. They contain components that are difficult or impossible to repair. They are designed to be replaced, not maintained. Planned obsolescence, the deliberate design of products with limited functional lifespans, is a well-documented feature of modern manufacturing. The rotary telephone was designed for the opposite. It was designed to last indefinitely. It had no components that wore out rapidly under normal use. The carbon granules in the transmitter compacted gradually over years, but they could be replaced. The dial mechanism's governor could be adjusted. The contacts could be cleaned. The cords could be replaced. The housing was made from materials that did not degrade significantly over time. The Bell system's own records show telephones remaining in continuous service for 20, 30, and in some cases 40 years or more without requiring replacement. The same physical telephone, with the same dial and the same handset, serving the same household through changes of wallpaper, through children growing up and leaving, through decades of daily use. This durability was not a marketing feature. It was an economic necessity. The telephone company owned the phones and bore the cost of replacing them. Every phone that lasted an extra decade was a decade of avoided manufacturing and installation expense. The incentive structure rewarded durability in a way that the modern consumer electronics market does not. The result was an object that achieved a kind of material permanence rarely seen in mass-produced consumer goods. Rotary phones from the 1950s are still functional today, not as museum pieces wired to simulate operation, but as actual telephones, capable of making and receiving calls on any network that still supports pulse dialing. The mechanical components are still within tolerance. The electrical components still function. The dial still generates clean pulses at the correct rate. The carbon transmitter still modulates current in response to a human voice. 70 years. That is how long some of these phones have been working. 70 years of daily use, of being picked up and put down, of dials being spun and handsets being pressed against ears. No software updates, no battery replacements, no charging cables, no cracked screens, no obsolescence. It is difficult to think of any other mass-produced consumer device in history that has demonstrated comparable functional longevity. And it raises a question that is more philosophical than technical. What was lost when we moved from objects designed to last to objects designed to be replaced? The cultural legacy of the rotary phone extends beyond its engineering. The device left marks on language, on behavior, on the way people think about communication, that persist long after the physical object has disappeared from daily life. The phrase dialing a number survives, even though no one dials anything anymore. We press buttons, we tap screens, we speak to voice assistants, but we still say dial. The word has detached from its mechanical origin and become a general synonym for initiating a telephone call, a linguistic fossil preserving the memory of a circular motion that most living people have never made. The phrase off the hook meaning overwhelmed or extremely busy or out of control, originates directly from the telephone. A phone that was off the hook could not receive calls. Its line was occupied. The exchange saw it as busy. The phrase migrated into general usage with a meaning that preserves the original sense of unavailability, even if most people who use it today have never seen a hook switch. The phrase hang up, meaning to end a call, refers to the physical act of placing the handset back onto the cradle, which in many early telephones involved literally hanging the earpiece on a hook mounted on the side of the phone. We still say hang up when ending a call on a device that has no hook, no cradle, and no physical action associated with ending the call beyond tapping a red circle on a glass screen. Even the word phone itself, from telephone, from the Greek for far sound, carries within it the assumption that the primary function of the device is to transmit voice across distance. Modern smartphones are used for voice calls perhaps 10 or 15% of the time. They are cameras, messaging platforms, web browsers, navigation devices, music players, social media terminals, and pocket computers that incidentally also make phone calls. Yet we still call them phones, because the telephone defined the category so thoroughly that its name became permanent. The rotary phone also shaped social behavior in ways that are easy to forget. Because the phone was fixed to a wall or a table, connected by a cord to a jack, telephone conversations happened in specific places. Families had a phone spot: the hallway table, the kitchen wall, the desk in the study. Long conversations required standing in that spot or sitting nearby, tethered by the coiled handset cord. Privacy was limited. Other family members could hear your half of the conversation. Teenagers, desperate for privacy, would stretch the handset cord to its absolute limit, pulling it around corners and into closets, which is one of the reasons those cords became so hopelessly tangled. The sound of a rotary phone ringing was a distinctive feature of domestic life for decades. The mechanical bell, driven by the electromagnetic ringer responding to the alternating current ring signal, produced a sound that was loud, clear, and impossible to customize. Every phone sounded essentially the same. There were no ringtones, no musical alerts, no vibrations. Just the bell, ringing in its 2-second bursts, audible throughout the house and sometimes beyond. That sound carried social weight. A ringing telephone demanded a response. Unlike a letter, which could sit on the table until you were ready to read it, or a knock at the door, which you could pretend not to hear. A ringing telephone created a sense of urgency that was difficult to ignore. Someone was calling. Someone was waiting. The longer the phone rang, the more insistent the summons felt. Not answering a ringing phone was, for many people, psychologically uncomfortable in a way that ignoring a text message or letting a call go to voicemail simply is not. This was partly because, in the rotary phone era, there was no answering machine for most of the period, no voicemail, and no caller ID. If you did not answer, the call was simply lost. The caller would have to try again later, and you would never know they had called. A missed call was a missed connection. And in an era when long-distance calls were expensive and sometimes difficult to place, missing one could mean missing something important. The answering machine, introduced commercially in the 1960s and becoming widespread in the 1980s, changed this dynamic. Caller ID, introduced in the 1990s, changed it further. But for the majority of the rotary phone's lifespan, the telephone operated on a simple, somewhat demanding social contract. When it rings, you answer. The network that supported the rotary phone, the copper local loops, the exchange buildings, the switching equipment, the trunk lines, the operators, the technicians, the splicers, the engineers, has not entirely disappeared. Copper local loops still connect millions of premises to the telephone network, even in countries where fiber optic broadband is rapidly expanding. Many of these copper pairs are the same physical wires that were installed decades ago, still carrying signals, still maintained by technicians who climb poles and enter manholes much as their predecessors did. But the system behind those copper pairs has changed beyond recognition. The calls that travel over them are no longer routed by electromechanical switches clicking through their sequences in windowless exchange buildings. They are processed by digital switches, by software-defined networks, by Internet protocol routing systems that bear no mechanical resemblance to the Strauger switches and crossbar frames that preceded them. The voice signals that once traveled as continuously varying analog currents through unbroken copper circuits are now digitized, sampled thousands of times per second, converted into streams of binary data, compressed, packetized, and routed through fiber optic networks and data centers, along with billions of other data streams. The analog telephone call, in its original form, has been largely replaced by digital approximations of varying quality. Some argue that something was lost in this transition. The analog telephone call had a quality, a warmth, a presence, an intimacy that digital voice communication does not always replicate. The bandwidth limitations of the carbon microphone and the analog circuit gave the telephone voice its characteristic sound, and that sound became associated for millions of people with the experience of human connection across distance. A phone call sounded like a phone call. It sounded like someone speaking to you from another place. And the slightly compressed, slightly narrow quality of the sound was paradoxically reassuring. It meant the connection was working. The system was functioning. The other person was there. Modern digital phone calls, particularly those made over Internet protocol systems, can vary widely in quality. At their best, they offer a wider frequency range and a clearer sound than analog calls ever did. At their worst, they suffer from compression artifacts, packet loss, latency, and the occasional robotic distortion that makes the speaker sound like they are talking through a malfunctioning radio. The consistency that characterized the analog telephone network, the fact that a call sounded essentially the same whether you were calling next door or across the country, has been replaced by a variability that depends on bandwidth, network congestion, codec selection, and a dozen other factors that the caller cannot see or control. The rotary phone itself did not cause these changes. It was merely the endpoint of a system that evolved past it. But the phone's disappearance from daily life coincided with, and in some ways symbolized, a broader shift in the way human beings relate to communication technology. The telephone, in its rotary dial incarnation, was a single-purpose device. It made phone calls. That was all it did. It could not send text messages. It could not take photographs. It could not browse the internet. It could not distract you with notifications while you were trying to concentrate on something else. When it sat on the table, silent, and unused, it demanded nothing of your attention. When it rang, it demanded all of it. Modern communication devices are the opposite. They are multi-purpose, always on, always connected, always capable of interrupting whatever you are doing with a notification, an alert, a message, a reminder. They sit in your pocket, vibrating and glowing, pulling your attention in multiple directions simultaneously. They are extraordinary tools, capable of things that the designers of the rotary phone could not have imagined. But they are not calm. They are not patient. They do not wait quietly on the table until they are needed. The rotary phone waited. It sat, solid and inert, as heavy and as patient as a stone, until the moment someone picked it up or the moment someone called. In between, it was simply furniture, part of the room, background, nothing more. There are people who miss that. Not many, perhaps, and not always for reasons they can articulate clearly. But the rotary phone represented a relationship with technology that was bounded, specific, and manageable in a way that modern devices are not. You knew what it did. You knew how it worked. You knew its limitations. And within those limitations, it worked perfectly, every time, for decades. Here is a final thought about the rotary telephone and the system it was part of. The telephone network, at its peak, was the most reliable communication system in human history. It operated 24 hours a day, 7 days a week, through storms, earthquakes, floods, and power failures. It connected any subscriber to any other subscriber, anywhere in the country, usually within seconds. It required no training to use, no manual to read, no software to update. It was available to virtually every person in the developed world, regardless of age, education, technical ability, or economic status. It was built by hundreds of thousands of workers over the course of a century. Engineers who designed the switches and the circuits, operators who connected the calls, linemen who strung the wire and maintained the poles, splicers who joined the cables, technicians who maintained the exchanges, planners who designed the numbering systems and the traffic models, manufacturers who built the phones and the equipment, and the managers who coordinated all of it into a single functioning system. The result was something that most people used every day without ever thinking about: a dial tone, a ringing phone, a voice from far away, sounding close enough to be in the next room, a connection made instantly, reliably, transparently, by a system so well engineered that its very success made it invisible. The rotary phone was the human face of that system, the part you could see and touch and hold against your ear, the part that sat on your table and became, through years of use, as familiar as a piece of your own furniture. It was not a computer. It was not smart. It did not learn your preferences, or track your habits, or sell your data. It was a piece of carefully designed engineering, made of plastic and copper and carbon and springs. And it did one thing, connecting your voice to another human being across any distance, with a simplicity and reliability that we have not, despite all our technological progress, entirely managed to improve upon. The next time you see one, in a museum or an antique shop or a grandparent's house, pick it up if you can. Feel the weight of the handset. Put your finger in one of the dial holes and pull it to the stop. Listen to the satisfying mechanical sound of the return stroke, the governor controlling the speed, the spring doing the work. What you are holding is not just an old phone. It is a piece of one of the most extraordinary systems ever built. A system that changed the way human beings live, work, communicate, and understand distance. A system that was conceived in the mind of a Scottish teacher of the deaf, refined by a Kansas City undertaker, built by an army of engineers and workers, and operated, for most of its history, by young women sitting at switchboards in rooms that most people never saw. It worked while you slept. It worked while you were away. It worked when the power went out and everything else stopped. And when you needed it, it was there, on the table, waiting, ready. All you had to do was pick it up and dial.